Origin of the Universe, Part 2. Let's have a little look at where we got to. So last lesson, we discussed that we had got some data that seemed to suggest that the only sensible interpretation of it was that the fabric of space itself was this stretchy material almost that Einstein had predicted would be expanding. And now Hubble has obtained some data using starlight from distant galaxies. And he has pieced together detective style the idea that this is true, that the space between the galaxies is expanding, carrying the galaxies further away from each other. This is a massive claim. People have been looking up at the night sky for millennia, and it always just looks the same. We've just always kind of believed that it's just always been like that it doesn't really change very much. And yet here are these scientists who are claiming that the entire universe is getting bigger and always has been. These are big claims. So we better check to see if there's any other evidence apart from the clever ideas of some genius and some shifted black lines on some pictures that were taken with a telescope. When you boil it down to that, it seems a little bit tenuous for such a big idea. So we better think about, are there any more evidence? We should ask some big questions like, is it even true? And if it is true, then why is it happening? Why should we live in a universe that behaves like this? But more so, the biggest thing, we should ask, what are the consequences of this idea? If it's true, what does it mean in a way that is going to affect us and our beliefs? So let's have a little start there, shall we? Let's think about the consequences, because that's the exciting bit of today's story. So here we go. Well, the idea is that if the universe is getting bigger, then yesterday it was smaller. And the day before that, it was smaller still. Last year, it was a lot smaller. 1,000 years ago, 1,000,000 years ago. How far do we need to go into the past before we start finding that the universe was actually very small indeed? Well, it turns out that the magic number is just under 14 billion years. Just under 14 billion years ago, the entire observable universe, that's everything that we can see through a telescope, the whole lot of it, billions of light years across, billions of light years across, all of it would have been so small that you could have held it in your hand, which is a staggering thought. The entirety of everything in your hands 14 billion years ago. Now, we should just make the point that I deliberately used the word observable universe there, because we tend to think that the actual universe is probably a lot bigger than the bit we can see. And that comes back to the cosmological principle again. We are obviously at the center of our own bubble. That's kind of our location within our bubble. And so when we look outwards, we see the edges of our bubble with us at the center of it. But somebody looking up through a telescope, orbiting a star on the edge of our bubble, will presumably be able to see further in the direction that's away from us than we can, because they're a lot closer to it. So we tend to think that the entire universe is hugely bigger than the observable universe. It may even be actually infinite in size. So when I'm saying that the universe contracts down and gets very, very small, that doesn't mean that it becomes in its entirety the size of an apple. It just means the bit we can see becomes as small as an apple. It may well be that there's a huge amount of universe beyond what we can see. That means that even when our bit of the universe shrinks down to the size of an apple, the universe may still be infinite in size. It's just everything's a lot closer than it was before. So pictures like the one on the screen, which I've kept because I like it, give the impression that maybe the universe boils down to a tiny little dot. But that's misleading. We have no reason to believe, I mean, it might be true, but we have no reason to believe that the universe would have in its entirety been the size that you could hold in your hand. Just the bit of it we can see. Okay. You might be wondering how you can fit a few 100 million galaxies into the palm of your hand. And that's because Einstein, who contributed quite a lot to science, it has to be said, also had a great idea that what we call energy and what we call matter are kind of interchangeable. I'm sure you've heard of his equation, E equals mc squared, but you may never have actually paused to think what it means. And what it does mean is that a lump of matter, m, say 3 kilograms, can be converted into some energy, E, in joules. You just need to find a process that does it. And actually, when we were talking about nuclear fusion and nuclear fission, and I said that energy is released in fission events and fusion events, including in the heart of the star, it's because processes are taking place in which matter goes missing from the universe. And it goes missing because it liberates itself as energy. The light and the heat that's coming out of our sun is energy that used to be the mass of some protons. I told you that protons fuse together to make helium. Well, if you take 4 particles and mash them together to make a helium nucleus, four hydrogen nuclei, and mash them together to make a helium nucleus, those 4 hydrogen nuclei have a greater mass than the helium nucleus does. Some mass went missing during the fusion event. And by E equals mc squared, it got converted into energy, and that is the heat and the light that's coming out of the stars. Well, we believe that 13.77 billion years ago, the universe was so small that at that point in its history, everything inside it was pure energy. And that as the universe expanded, the energy turned itself into matter. And we'll come back to that idea in a minute. So it's not the case that hundreds of millions of galaxies would have been able to fit into the palm of your hand. Those galaxies at that point in the history of the universe would have been pure energy. They haven't yet turned into matter and haven't yet coalesced into galaxies. If you convert the amount of matter in the observable universe into energy and then put it all in a small volume and ask how big it is in temperature, it comes to billions of degrees. So this patch of universe, this small patch that we're trying to hold in our hands, not that we could be there, it's going to be a little bit too hot to hold. 1 billion degrees. That's a crazy amount of energy. And then, like a fireball, like an explosion is the way that it's often portrayed, the whole thing expanded, like lighting the touch paper on a bomb and the bomb exploding outwards with all of that heat. But that's a poor picture of what we're talking about here. There's no explosion. There's no known cause for there to be all this energy in one place, and no known cause for why it expanded. The first scientist who pieced this together was actually a priest, and he he actually attributed this moment to the bit in the Bible that says, "Let there be light." And I know friends who are practicing cosmologists who have a real deep down belief in God and the Bible, which you might think, the two are natural opposite views, but some cosmologists really do believe that this was kind of the God moment. Many cosmologists don't, of course. So we don't know why the universe began, well, the observable universe began small and hot and expanding, but it was. On your screen, well, that's what the evidence points out. On your screen in front of you is a link, that little graphic. If you click on it, if you pull up the PowerPoint later, to a Minute Physics video. If you've never watched Minute Physics, you are missing out big time. That talks about the fact that the universe might still be infinite, even though the observable bit of it might have begun in a very small patch. So, this moment, 13.77 billion years ago, could be considered to be the birth of the universe. Certainly our bit of it. If we assume that the entire universe is infinite, then every patch of the universe would have been small and turned into billion-degree energy. And so the entire universe, even if infinite, would have been in this maelstrom of hotness and energy and expanding. So it's as good a beginning as we're going to get, because nothing existed at that point except pure energy. And from it came the universe as it is now. Energy turned into matter, matter turned into galaxies, and eventually up popped us to have a look at it. Prior to that point, even if anything had existed prior to that point, it had been obliterated. And so it's a meaningless question to ask what happened before that hot, dense state, because whatever did happen, if anything at all, was completely destroyed and can never be known. And so it's a meaningless question to ask what happened before 13.77 billion years ago, when the universe was pure energy. There is no before. Even if there was a before, it no longer exists and can never be known. And so it's effectively a beginning to the universe, even if it wasn't actually a beginning to the universe. Okay. This idea, when built upon merely redshift data, was not widely liked. It was too out there, too crazy. And around about 1950, 1949, it was becoming known in the public sphere. And this very famous astronomer, Fred Hoyle, he went on BBC Radio, and he was against this notion that the universe began in a hot, dense state and has been expanding ever since. He thought that this was a silly idea, and he really wanted to bring it home to the British public on this BBC radio broadcast that he felt that this was a stupid idea. So he tried to belittle it by giving it a silly name, and he referred to it as this Big Bang. And he thought he was doing his best to kill off the theory, but in actual fact, he had no understanding of the great British public and how much they would love that it was called the Big Bang. It was a really catchy name that, to a layperson who knew nothing of science and nothing of cosmology, they could really get their head around. Oh, it's a Big Bang. And the idea stuck. And to this day, we refer to the leading scientific theory of the origin of the universe as the Big Bang, which is amusing to me and to lots of other people as well. I suppose you should never take yourself too seriously. It's a misleading name because nothing banged. Like I said, there was no explosion. It's just the beginning of a big expansion. So it's really the big beginning of an expansion. But Big Bang is never going away. We're never going to lose that name. Okay, so we've got a consequence, but let's return to the idea of, is it right? Because we just claimed that we knew the beginning of the entire universe. And all we've got at the moment is that it is based upon some black lines on a spectrograph of some starlight. So we better do better than that. This is the beginning of the universe we're talking about. So what else do we know? Well, once you accept the Big Bang theory as a possibility, you can then ask, well, what are the consequences of it? So in particular, if we're going to wind the clock back and turn all the matter into energy, and then hit play and let it run forwards, we should be able to predict how the energy turns into matter, which turns into stars and galaxies and all the rest of it. We should be able to model that. And there are some brilliant supercomputers on the planet that have done exactly that. They have made videos, you can get them on YouTube, where they show the energy turning into matter, the matter collapsing into stars and galaxies and spirals and chains of galaxies and clusters, and it's brilliant. And they've done remarkable work with their simulations, but we don't need to go that far. You see, even a simple treatment of the Big Bang theory, which talks about how the energy turns into matter, predicts that it's not a 100% conversion process, that only some of the energy turns into matter, and that some of it will be left behind. And that energy will be zipping around everywhere. Every square millimeter of space will have a little bit of this original energy zipping through it, like light. But really, really, really low energy light. Because if we think that the energy of the universe was up around 1 billion degrees when it was small, well, it's a lot bigger than it used to be. And all that energy has become diluted over a much bigger volume. And so it's not at 1 billion degrees anymore. If the sky was at 1 billion degrees, it would be brighter than the sun. It's black. There's no visible light zipping around in every millimeter of space. And that's because, and we spoke about this when we were doing the waves topic, that the color of light corresponds to the temperature of the object releasing the light. And we now believe, the Big Bang theory predicts, that if you take that 1 billion degrees and you dilute it down over the size that the universe has become now, it's down at minus 271 degrees, just above absolute zero. In fact, the prediction is that it's 2.73 Kelvin. And if you turn that temperature into a wavelength of light, it corresponds to microwaves. So the Big Bang theory predicts that the blackness of space is only black in the visible spectrum, that every tiny, tiny, tiny little patch of space has actually got microwaves whizzing through it, corresponding to this tiny little temperature of 2.73 degrees Kelvin. But this was back in the 50s and 60s, and we never really launched anything into space, certainly not a thermometer. So how could we go about doing this? Okay, well, you need to meet these guys. These are Doctors Penzias and Wilson. They're very educated people, and they've got jobs working in the research division of AT&T, which is America's version of British Telecom. They're in the research wing because they're pushing at the boundaries of what telecommunications can be. And they've got this cool idea that they can do away with wires. America is loving the telephone and making conversations, but America's a big place, and laying cables from the East Coast to the West Coast is taking a lot of time, money, expense, maintenance. Couldn't they do without the cables? They've got this idea that they could broadcast telephone signals wirelessly. Wow, who'd have thought? You couldn't imagine life, I'm sure, without a mobile phone in your pocket today. But they had the idea, and they've built that thing, a massive horn that they are using to collect the microwaves that they are broadcasting from a couple of thousand, I can't remember how far away, but you know, about 1,000 kilometers, something like that. And they're trying to catch it in that horn. And they're doing really well, actually. They can kind of hear somebody's voice coming through, and they're getting very, very excited. They are about to revolutionize telecommunications. It's just, when they're trying to listen to what's coming through, it's just got this really annoying hiss in the background. So somebody's talking, and then over the top of it, all they can hear is shh, and it's driving them nuts, because no customer on the planet is going to put up with that, and it's holding them back from revolutionizing telecommunications. They tried, they really did. They painted the thing, they cleaned the thing, they even cleaned out some pigeons that were nesting in it, in the thing, thinking that maybe the pigeon poop was obstructing their signals or something. In the end, they couldn't work it out. So they telephoned the local university, and they got put through to this guy. His name's Robert Dick. And for the life of them, they really couldn't understand why them mentioning that they had this really annoying hiss in their microwave detector was making the guy at the other end of the phone so excited. And he jumped straight in his car and he drove straight down to them right there that afternoon with the biggest smile on his face, because he'd been looking for exactly that. Robert Dick's a cosmologist, and he's been searching for the microwaves. And what Penzias and Wilson have done is built a machine that can detect these microwaves raining down from space. That annoying hiss is the leftover energy of the Big Bang itself, and they just detected it. It's now known as the cosmic microwave background radiation, and we have sent satellites up into space and made a map of it. This is a map. It's a bit like a globe when they stretch it flat. So here's a flat projection, but now we're inside the globe. So we're looking out into the universe. So we're inside a spherical shell of the universe. We're at the center of it, and we're looking outwards at the sphere that's around us. And then we've projected it onto a flat map. So that's what the picture shows. You'll notice some bits of red, some bits of pink, some bits of blue. Those are the ever so slight temperature differences. But all of those temperature differences are down at less than 1/100th of a degree. And they are all at around about 2.7 Kelvin. Penzias and Wilson shared the Nobel Prize in 1978 for discovering the afterglow of the Big Bang itself. Dick got nothing, even though he was the one that was looking for it, and they were the one that accidentally found it. Nobody ever said the Nobel Committee was fair. Okay, this is evidence piece number 2. The Big Bang Theory predicts that there will be microwaves everywhere in the sky, corresponding to a temperature of about 2.7 K. And we've built machines that have found it, 2.73 K, exactly as predicted. But what else does the Big Bang Theory predict? The process of turning energy into matter is sometimes referred to as nucleosynthesis. And that theory predicts that when the energy turns into matter, it would do so in such a way that 75% of the matter in the universe will be hydrogen and 25% of it will be helium. Now, this is primordial matter. as in matter that was made in the Big Bang, or a couple of 100,000 years after the Big Bang, as it cooled down enough to do so. We have already done the story of stars, and we have seen how stars are these nuclear furnaces which produce the elements on the periodic table, and that when they supernova, they cast those elements out into the sky. So we're not suggesting that everywhere is 75% hydrogen, 25% helium. Anywhere where there's been a supernova at all is going to have a different ratio. So we need to go pointing our telescopes at patches of the universe that haven't had any supernova. And the way to do that is to find the oldest, no, that's the wrong word, the furthest away galaxies from us. Because remember that light takes time to travel across the sky. And so if we point our telescopes at something that is right on the edge of what we're capable of seeing, then the light that we're looking at has been traveling across the universe for 13 billion years. And so when we look at far away, we're looking into the deep past of the universe. And so the furthest away stars are the youngest stars. They're the ones that were made first, released some light, and those stars are long since gone, but the light from when they were young is still traveling across the universe and is still what we're detecting today. So when we point our telescopes at the furthest away stars in the furthest away galaxies, we are seeing the earliest matter in the universe. And when we use our spectroscopy techniques to have a look at the spectra from this starlight, it only has the lines of hydrogen and helium in it. And the relative, well, I was going to say brightness, but dimness of those lines gives us an indication of the relative abundance. And it does correspond to 75% hydrogen, 25% helium. Something like that. It's very, very close. And so we have our third piece of evidence. The redshift data suggests that the universe right now today is expanding, which coupled with Einstein's general theory of relativity suggests that the universe was once a lot smaller and hotter. And then if we allow it to expand in our model and cool down, it predicts a final temperature of the universe today, which has been experimentally verified, and it predicts a ratio of matter in the universe that has been experimentally verified. These three pieces of evidence are utterly independent of each other, and they all perfectly match the predictions of the theories that ultimately are all anchored in the Big Bang theory. Did the Big Bang happen? I can't tell you it did. I wasn't there. Neither were you. No one was. All we can do with scientific theories is to put forward an idea and ask that idea what predictions it makes, and then go obtain some evidence that supports the truth of the predictions. That's what we've done. We've taken an idea, we've made three separate predictions, we've tested each one, and each one has come true. This is no guarantee, but it's all about weight of evidence. At some point, even in legal trials, you have to accept that you have obtained enough evidence to believe in the theory that you're trying to argue. And that's the point we're at now. There are scientists on the planet who think it would be cool to come up with an alternative to the Big Bang theory. And there are alternatives, but none of them can hold their own yet against the Big Bang theory. But what's important is that whereas in lots of fields of science, there is competition and different research groups are genuinely trying to compete to find the best explanation for something, the people who play the game of what's an alternative to the Big Bang are kind of doing it tongue-in-cheek. It's a fun idea to play with, but there aren't really any serious scientists on the planet who actually believe that they are going to find an alternative to the Big Bang theory. It is mainstream accepted. And what Hoyle referred to as the Big Bang is our origin story of the entire universe. There remain questions, of course. Here are some common ones. There is no outside. The universe isn't expanding into anything. This might be because it's infinite in size. And so the bit that we consider to be a small apple-sized sphere that we can hold in our hand, that's just the observable bit. There's a whole load more outside it that wouldn't fit in our hands. Or maybe the universe isn't infinite. It's just so utterly big that we can't see the edges of it. And therefore, even if there was an outside, we can never, not even in principle, know anything about that space. And therefore, philosophically, it's a meaningless question. If it in principle cannot be answered, it's not a question that science is interested in. Nor is there a before the Big Bang. I've already covered this a little bit, but either the universe really did begin in a tiny little point that then expanded outwards, or there was a universe, but somehow it got collapsed and destroyed and turned into energy, and then it boinged back out into a new universe. But in either of those interpretations, any knowledge of what came before 13.77 billion years ago is unobtainable. It was destroyed in that hotness of what we call the Big Bang. And therefore, again, it's another meaningless question. If you can't in principle answer it, science isn't concerned with it. There is no center to the universe in the same way that there can't be any edges. If there can't be any edges, then you can't find a middle. So the universe isn't expanding away from a central point. There is no one place that you can consider the entire universe to have exploded from. There is no place where the Big Bang occurred. The Big Bang was everywhere. Everywhere started stretching all at the same time. There is no middle from which the expansion is occurring. There are, and there's a video on that screen that goes over some of those things with you. There are some more mysteries, though. Just before you were born, which is very, very recent in scientific terms, we got good enough at our measurements of distances and redshifts that we discovered something completely unexpected, which is that the universe appears to be accelerating in its rate of expansion. It's not just that it's expanding at an accelerating rate. This is not something that we built into the Big Bang theory and not something that Einstein's general relativity predicts. So either our measurements are wrong, and they might be, but we have spent 20 years trying to show that they're wrong, and we haven't managed to do so. It does appear to be genuinely true. And so the question becomes, what did Einstein miss out of his general relativity? What could possibly be providing the extra kinetic energy to drive an accelerating expansion? So it's been called dark energy, but you need to understand fully that that is just a placeholder for we have no idea. It just sounds kind of better on grant applications when you want the government to fund you some more research, to write that you would like to do research into dark energy rather than you would like to do research into this thing that we have no idea what it is yet. So giving it a name is something that scientists like to do, but I wouldn't want you to think for a second that anyone on this planet has the first clue about what dark energy is. It's just a placeholder for unknown thing that is causing the expansion of the universe to accelerate. It was given its name following on from dark matter, incidentally. I showed you a picture last lesson of red-shifted and blue-shifted opposite sides of a spiral galaxy to demonstrate to you that spiral galaxies don't just look like they're spirals, but are actually spiraling. They're spinning. What I didn't tell you at the time was that they are spinning way too fast. If we look at the amount of starlight coming out of a galaxy, we can make a pretty good estimate of how much star activity is happening inside the galaxy, and therefore we can make an estimate of the amount of mass that's in all of those stars. So we're pretty good from judging from starlight's brightness how much mass must be present to represent all of those stars that are producing all of that light. It's nowhere near enough mass. I mean, seriously, it's like 4% of the mass that would be required to provide enough gravity to allow the stars at the edge of the galaxy to be orbiting at the speed they're orbiting at. There just is not enough gravity from the galaxy to hold on to stars that are orbiting that quickly. So either we screwed up our theories of gravity, which is possible on a galactic scale, or there's some more matter out there amongst the stars, but it's not glowing. It's dark matter. And again, it has this big romantic name, like it's weird or something, and it might be, but all you need to focus on is it's matter that's not glowing. It's not luminous matter. It's a bit more complicated than that, because as the starlight from stars passes through it, it would absorb it a little bit and start to glow. That's not happening either. So it's not just that it's not fusing, it can't actually interact with light. So if I were to bring some dark matter in and put it on the table in front of you, you would be able to see straight through it. It would be transparent because it doesn't interact with light at all. So it is a slightly weird stuff. We have some scientific ideas about what it could be, but we've never actually held a pot of it in front of us, so we don't know what dark matter is either. But those are the two big mysteries in cosmology today. What is the extra mass that's allowing the galaxies to spin faster than they should be spinning? And what is the source of the energy that is allowing the universe to accelerate in its expansion? And there's a video on the screen there that you can click the little thumbnail and you can listen to that. And there's also, if you prefer, a link there to a podcast that you can listen all about it. Okay, what about the future then? Well, the future is dark in more ways than one. Sometimes the current era of the universe is referred to by science fiction writers as the brightness. It's the era of the universe after the matter was created and it coalesced into stars that fused and released heat and light. We're in the period in which matter is close enough together and there is enough hydrogen and helium for stars to fuse them and light us up. Life on Earth exists because of the sun's ability to fuse hydrogen into helium. But we've spoken about the fact that the hydrogen in every star will eventually run out. Some of the stars will go quietly away. Some of the stars will explode and cause further star formation. But one day, eventually, in the far, far, far future of the universe, there will be no more hydrogen left. It'll all be gone. And the stars will go out. Even before then, the expansion of the universe will have carried all of the other galaxies away from us. And they'll have disappeared further away than we can see. And so we'll lose the distant galaxies first, and then one by one, the lights in our own galaxy will go out until only darkness remains, which is a very sad way to think about the future of the universe. It's not projected to happen anytime this side of 100 billion years. Now, given the universe is only just older than 10 billion years, we've got 10 times the existence of the brightness before this happens. I don't think you and I need to be overly concerned about this. It's often referred to as the heat death of the universe, kind of because the heat leaks out of the universe. And it is a sad way to go. However, the person on your screen is Isaac Asimov, who is one of the greatest science fiction writers of all time. He predicted many things while he was writing during the 50s and 60s and early 70s. And science fiction buffs today, they still devour Asimov's books because he was just decades ahead of his time. And the things that he has predicted are only just coming true now. And in one of his books, a short story actually, that he personally considered to be the greatest thing he ever wrote, which is saying something given how much he wrote and how many awards he won and how he is considered to be the greatest scientific writer that has ever lived. For him to say that this is the story that he is proudest of means that if you are only ever going to read one thing that Asimov wrote in your entire life, make it this one. It's called The Last Question, and it deals with the heat death of the universe. And there are links on your screen in front of you. You can either download the book for free. It's only about 30 pages long. Or you can click on the YouTube link and have somebody narrate it to you if you don't like reading. Yeah. Asimov was hoping that the heat death might not be a thing that was inevitable. So have a little read of his story and see what he had to say about it.